All right, welcome back to Gradient Daily. Today, we are diving deep into a really cool paper that's making some serious waves in high-res 3D generation. It's called Sparc3D, Sparse Representation and Construction for High-Resolution 3D Shapes Modeling, and it's from Zihao Li and the team. Let's jump right in.
Okay, just look at this thing. Seriously, this isn't a photo. The detail is just insane, right? Every little wire, every single plate. This is the dream for 3D asset generation, but if you've ever tried to do this, you know the reality. Getting from a simple prompt or an image to this is a nightmare. It's a pipeline just full of compromises, lost details, and super frustrating glitches. So the big question this paper asks is, why is it still so hard? And more importantly, how do we actually fix it?
So before we can really get why the Sparc3D solution is so clever, we first have to get our hands dirty and understand the problem itself. We've got to look at the cracks in the foundation of how we currently build these 3D models, because that's where everything starts to go wrong. The core issue when you boil it all down is that we're just losing information. You know the standard process, right? It sounds great on paper. You take a VAE, a variational autoencoder, to squish a complex 3D model down into a neat little blueprint. Then, a diffusion model comes in and learns how to create new blueprints. But here's the thing. That process is leaky. It's like a bad zip file. Critical details just disappear. Sometimes whole chunks of the model just vanish into thin air. And the paper says, hey, there are two big reasons for this. Something they call a modality mismatch and a whole bunch of really destructive steps that happen before the AI even gets to see the model. And this right here, this shows you the damage perfectly. On the left, you've got the original, clean 3D model of a car. Looks great. On the right, that's what happens after it goes through one of these old-school processing pipelines. See anything, missing? Yep. The entire back wheel is just gone, wiped out. And this isn't the AI's fault. This is a data prep problem. It's exactly like they say, garbage in, garbage out. You can't give a brilliant artist a blurry, ripped photo and expect a masterpiece. So how in the world does a whole wheel just disappear? Okay, let's walk through this broken pipeline step by step. First, you take the raw model and sample it into something called a UDF, an unsigned distance function. That just tells you how far away any point in space is from the surface. But for an AI to get it, it needs to know what's inside versus outside. For that, you need a signed distance function, or SDF. And here's problem number one. The way they used to convert UDF to SDF was basically a cheap trick that instantly cut the resolution in half. Boom. All your fine details gone. Then they use a process called marching cubes to build a mesh, but that creates this weird double-layered surface. So what's the fix? Another cheap trick. They just tell the computer, hey, find the biggest single piece of this mesh and delete everything else. It's just a brutal, dumb approach. It assumes any little detached part is just junk when it could be a side mirror or an antenna, or, you guessed it, a wheel. And poof, it's gone. You can see how every step just makes the problem worse and worse. Okay, so that's the mess we're in. The input data is getting totally mangled before the AI even sees it. The Sparc3D authors knew that if they wanted a better generator, they had to start with a better blueprint. And that brings us to their first huge idea, a totally new way to represent 3D shapes called Sparcubes. The best way to think about it, it's like smart digital clay.
So, what are Sparcubes, really? Well, the full name is Sparse Deformable Margin Cubes. Let's unpack that. Sparse is huge. It means it doesn't waste time and memory on all the empty space around an object. It just focuses on a tight little band of voxels right on the surface. That's how they can hit this crazy 1024 cubed resolution without, melting your GPU. Then you have deformable, and this is the really magical part. Instead of a stiff grid where the shape has to snap to the grid lines, the grid itself is flexible. The little cubes can actually move and stretch to perfectly hug the real surface. It's literally like sculpting. And what you get at the end is this beautiful, high-res, watertight model that's ready to go. So how does it work? Well, it starts by being smart. Instead of making a giant grid that's like 99% empty space, the algorithm first finds just the active voxels, this thin shell right around the object, and it only does its calculations for those voxels. This whole sparse idea is the key to why it's so efficient. It's how it can handle these super high resolutions without just crashing.
Okay, next up, it needs to figure out what's inside and what's outside. And for this, it uses a really clever flood fill trick. Imagine starting at the corners of a box around the object and just pouring in a label. Everything that gets wet is the outside. Whatever stays dry on the inside, well, that's the inside. This lets it create that all-important sign distance function without that horrible resolution-killing hack we talked about before. It's just so much smarter and doesn't lose any detail.
And here, this is where that digital clay idea really clicks. See, instead of just tweaking the numbers at the corners of a fixed grid, the Sparcubes method does something way more intelligent. It actually moves the corners of the grid themselves. The whole grid literally bends and warps to perfectly match the original model's surface. It's optimizing the geometry of the grid, not just the values on it. You just can't get that level of accuracy with a stiff, boring grid. And then, for the perfectionists out there, there's one last optional step. Because this whole thing is differentiable, meaning you can use calculus on it, you can actually render 2D pictures of the Sparcubes model, like a depth map. Then you compare that picture to a render of the original model. If there's any difference, the system uses that to make one final set of tweaks. It's basically a last-minute quality check to make sure the model doesn't just have the right numbers, but that it actually looks right from every angle.
Okay, so now we have this amazing, super high-res, almost perfect 3D blueprint. Awesome. But that's only half the story, right? We still need a VAE that actually understands this new format, one that can squish it down and build it back up again. And that leads us to the second core piece of Sparc3D, the Sparcon-VAE.
So what's the big deal here? It all comes down to fixing what the paper calls the modality mismatch. Think about it like this. The old VAEs were like terrible translators. You'd give them a sentence in one language, like a bunch of 3D points, and you'd ask for it back in a totally different language, like a grid of SDF values. To make that translation work, they had to use these super complicated, slow, and clunky attention mechanisms. It was a mess. But the Sparcon-VAE, it's totally different. It's modality consistent. It's like a Fluent native speaker. Because it uses the same language for both input and output, it takes in Sparcubes and it spits out Sparcubes. No translation needed. This means it can use these really fast, lightweight tools and nothing gets lost in translation.
Okay, the theory sounds fantastic, right? A better blueprint, a custom-built VAE, it all makes sense. But the real question is, does it actually work in practice? Well, this is where the rubber meets the road. Let's look at the results and see how Sparc3D does in a direct showdown with the old champ.
First, let's look at the raw numbers for just the remeshing part. Turning a messy model into a clean one. Check out the results on the wild dataset. This is a tough one. We're looking at chamfer distance. Lower is better here. The old method gets a 63.7. Sparc3D gets, wait for it, 0.46. That's not just a little better. That's over 100 times better. It's a complete game changer. And look at the F1 score, which basically asks, did you keep all the good stuff and not add any junk? It's 97 for Sparc3D versus 66 for the old way. I mean, the numbers speak for themselves. Yeah, let's just put that F1 score on a chart because you really need to see it to believe it. On the left, that's the old state of the art. And on the right, that's Sparcubes. It's not even a competition. That bar chart shows you the difference between a system that's basically guessing and throwing away parts versus one that actually understands and preserves the original shape. This right here is the rock-solid foundation that everything else is built on. And here's what that crazy number difference looks like visually. Hey, remember our poor car that lost its wheel? Well, here it is again. On the left, the original model, and on the right, the output from the Sparcubes pipeline. The wheel is back, and not just the wheel, the grille, the spoiler. Every little detail is perfectly preserved. Nothing is gone. This is what a high-quality blueprint looks like, and it's what you absolutely need if you want to generate high-quality models. Okay, now for the main event, the full VAE reconstruction. Top row is the original, ground truth model. Bottom row is what the Sparcon-VAE spits out after doing its whole compression-decompression dance. And wow, the quality is just stunning. I mean, look at those paper-thin spokes on the Ferris wheel, the delicate little petals on the flowers. It handles these super tricky, complex shapes like it's nothing. This is what you get when you have a great representation and an architecture that's built for it. So yeah, the results are obviously incredible. Sparc3D is clearly setting a new standard here. But, no research is perfect. So to be fair and give you the whole story, let's take a balanced look at the strengths and also the limitations that the authors themselves point out. So let's run through the wins. First up, fidelity. It's just state of the art. It keeps the details better than anything else. Second, efficiency. It's way faster. We're talking 3x faster for remeshing and a 4x speed up for VAE training. That's huge for researchers. Third, the outputs are always watertight, perfect for 3D printing right out of the box. Fourth, the architecture is just smarter. It's lightweight and efficient. And finally, and this is a big one, it plays nice with others. It's designed to slot right into existing diffusion models, making them better without having to start from scratch. It's a total plug-and-play upgrade.
Now, on the flip side, the authors are really upfront about what it can't do. First off, this is all about the shape, the geometry. It doesn't handle textures at all. No colors, no materials. They chose to focus on solving the geometry problem first, which makes sense. Second, and this is a common thing with these methods, it throws away any internal parts. So if you have a 3D model of a car with a super detailed engine inside, this process will basically seal the hood shut and delete the engine. It only cares about the outside shell. So for things like engineering or medical scans where the inside is what matters, this isn't the right tool for the job. So let's step back for a second. What does a breakthrough like this really unlock for the future? I mean, when you can suddenly create incredibly detailed, complex 3D models this fast and this reliably, what happens? For gaming and VR, you're talking about building entire worlds that are way richer and more interesting in way less time. For robotics, it means creating much more realistic simulations to train robots. This isn't just some small improvement on a benchmark. This is a foundational technology that could totally speed up how we create 3D content everywhere.
All right, we have covered a ton of ground here, from broken pipelines to squishy digital clay and Fluent AI translators. So let's boil this whole thing down. If you walk away with just 3 key ideas from this paper, these are the ones. Takeaway number 1, representation is key. The whole magic starts with Sparcubes. It's just a fundamentally better blueprint that solves that garbage in, garbage out problem. Takeaway number 2, speak the same language. The Sparconv-VAE is so much better because it's fluent. It takes in Sparcubes and gives back Sparcubes, making it way faster and more accurate. And takeaway number 3, better inputs make for better outputs. It's that simple. By fixing the foundation, the blueprint, and the encoder, Sparc3D creates a much cleaner, higher quality canvas for all the amazing diffusion models out there to paint on. It lifts the entire field up. And that's our deep dive on Sparc3D. It's just a fantastic reminder that sometimes the biggest leaps forward come from going back and fixing the fundamentals. If you like this explainer and want more deep dives like this, make sure to subscribe to Gradient Daily. We'd really appreciate it. And be sure to check back tomorrow for our next paper presentation.